Hey guys, welcome back to my channel. Today we're going to be looking at AQA A-Level Chemistry, the first of the series. I'll be uploading videos for all of the content on AQA A-Level Chemistry, but today we are specifically looking at part 1 of physical chemistry. There is a lot of content, so each section is kind of split into 2 topics or 2 videos, just to make it a bit more bite-sized. But today we'll be looking at atomic structure, amount of substance, bonding, energetics, kinetics, equilibria, oxidation, reduction, and redox. So one thing that's really important is like a lot of this stuff is already covered, already stuff you know from GCSE chemistry. It's just a lot more obviously advanced to make it the A level. But we are just going to jump straight in. Also, before we jump in, of course, do the usual: subscribe, like, comment below any questions you may have that I'll either answer myself or your fellow students may get to it before I do. But yeah, if you find this helpful and you want to see what other videos I put up, then please subscribe. So just going straight in with atomic structure. So the model for atomic structure has evolved over time as knowledge and scientific understanding changes. So we've gone from the plum pudding model, which you can see in the top left corner, where it was kind of this idea that the atom was just this plum pudding, and the electrons and protons were just kind of moving around in there. But then obviously we have what we use now, which is next to that. So you've got obviously you've got the nucleus, which contains the protons and neutrons, and then the electrons in the energy shells. This is known as the electron shell model, which shows the atom consisting of a small, dense central nucleus surrounded by orbiting electrons in the electron shell. This was developed from the Rutherford scattering experiment in 1911. The nucleus consists of protons and neutrons, so it has an overall positive charge and contains almost the entire mass of the atom. As you can see in the little table in the top right, this obviously just looks at the relative charge and relative mass of each of these subatomic particles. The maximum number of orbiting electrons that can be held by any single shell depends on the number of the shell, and the general formula is 2n squared. So if it's shell 2, that'd be times like 2 squared times 2, Mass number, which uses the symbol A, is the sum of protons and neutrons, and the atomic number, represented by Z, is the number of protons / electrons, because this number is generally the same unless it's an ion that you're talking about, in which case it may be different. Relative atomic mass, so AR, is the mean mass of an atom of an element, divided by 1/12 of the mean mass of an atom of the carbon-12 isotope. So the key here with a lot of these kind of definitions at the beginning, everything is based off this 1/12 of a mean mass of an atom of carbon-12. Carbon-12 is essentially the basis for most of chemistry, most of science. So it's really important you remember that part of the definition. Isotopes are atoms of the same element with the same atomic number but different number of neutrons, so different mass number. For example, hydrogen has 1 proton and 0 neutrons, deuterium has 1 proton and 2 neutrons, and tritium has 1 proton and 3 neutrons. So they're variations of hydrogen and its isotopes. Then neutral atoms of isotopes react chemically in the same way, but because of the sharing, transfer of electrons is unaffected, but they do tend to have different physical properties. And ions are formed when an atom loses or gains electrons, meaning it is no longer neutral and will have an overall charge. And then you've just got a couple of little equations at the bottom as well, which are useful to know. Then further, we have mass spectrometry, which is an analytical technique used to identify different isotopes and find the overall relative atomic mass of an element. There's also another type, which is time of flight mass spectrometry, which records the time it takes for ions of each isotope to reach a detector, and so spectra can be produced showing each isotope. Ionization is when a sample of element is vaporized and injected in the mass spectrometer, where a high voltage is passed over the chamber, causing electrons to be removed, leaving +1 charged ions in the chamber. Just to note, with the time of flight mass spectrometry, that is the top diagram on the right-hand side of this slide. So you can just kind of if for those who prefer to like visually see things, that's what it looks like. These positively charged ions are then accelerated towards a negatively charged detection plate. The ions are then deflected by a magnetic field into a curved path. Radius of the path is dependent on charge or mass of the ion, which is known as ion drift. So this is all still talking about the time of flight mass spectrometry. When the positive ions hit the negatively charged plate, the gain in electron producing a flow of charge, the greater the abundance, the greater the current produced. These current values are then used in combination with flight times to produce a spectra printout with the relative abundance of each isotope displayed. During the ionization process, a 2+ charged ion may be produced, so will be affected more by the magnetic field, producing a curved path. Apologies for any spelling mistakes in this as well. Of smaller radius. The mass to charge ratio, so MZ, is halved and can be seen on spectra as a trace to half the expected MZ value. So you can see here on the right hand side, so the middle graph is an example of basically how this will look. Then you've got chlorine spectra is produced by the mass spectrometry of chlorine, displaying a characteristic pattern in a 3:1 ratio for chlorine plus ions and a 3:6:9 ratio for chlorine 2+ ions. This is because one isotope is more common than the other, and the chlorine molecule can form in different combinations. So this is similar to looking at the graph in the bottom right corner, this is how it would look for the chlorine spectra. Now moving on to electron configuration. So specifically, really looking at the electrons within the atom. So electrons are held in clouds of negative charge called orbitals. You've got an s orbital which holds 2, p orbital which holds 6, d orbital that holds 10, and f orbitals. These correspond with blocks in the periodic table, and each element in that block has outer electrons in that orbital. So you can see here in the periodic table on the right hand side, you can see how the S block is to the left, D block is in the centre, P block is to the right, and then F block is that little additional bit at the bottom. And you've also got the shapes here of what these kind of orbitals look like and how they work. See, the S orbital is spherical, P orbital looks like a bit like a dumbbell, or the classic infinity symbol, and the D orbital. So there are 3 rules I missed one there. The energy of the orbitals increases from S to D, meaning the orbitals are filled in this order. There are 3 rules for writing electron configuration. The lowest energy orbital is filled first. Electrons with the same spin fill up an orbital first before pairing begins. No single orbital holds more than 2 electrons. So here's an example of how you'd write it for sodium. So 1s2, so that's saying that the first s orbital is holding 2 electrons, then the second s orbital is holding 2 electrons, and then the level 2 p orbital is holding 6, and then the final 3s is holding 1 electron. Within an orbital, electrons pair up with opposite spins so that the atom is as stable as possible. Exceptions for this is that if electron spins are unpaired and therefore unbalanced, it produces a natural repulsion between the electrons, making the atom very unstable, and so the electrons may take on a different arrangement to improve stability. So an example of this you can see just below the periodic table diagram is that you've got these 2 on the right hand side in 2p. They are not paired, they are separate to allow some balance to make the element slightly more stable. And then you've got ionization energy, which is the minimum energy required to remove 1 mole of electrons from 1 mole of atoms in a gaseous state. Then the unit for this is kilojoule per mole. The successive ionization energies occur when further electrons are removed, usually requiring more energy because as electrons are removed, the electrostatic force of attraction between the positive nucleus and the negative outer electron increase, so more energy is required. First ionization energy follows trends with the periodic table, so along a period, first ionization energy increases due to a decreasing atomic radius and greater electrostatic forces of attraction, and then going down group, first ionization energy decreases due to increasing atomic radius and shielding, which reduce the effect of the electrostatic forces of attraction. When successive ionization energies are plotted on a graph, a sudden large increase indicates a change in energy level, and this provides supporting evidence for the atomic orbital theory. The first ionization energy of aluminium is lower than expected due to a single pair of electrons with opposite spins, so there is a natural repulsion which reduces the amount of energy required to remove the outer electron. In this bottom right corner, you can see it's quite small. Apologies for that. I kind of just sort of run out of space on this slide. But here's some key examples that you'll likely be asked to know, or just to help give you an idea of exactly what they're looking for in terms of, how many electrons it's got, how these are placed into the orbitals, and how you would write this as well. Then moving forward to amount of substance. So relative molecular mass, so MR, is the mean mass of a molecule of a compound divided by 1/12 of the mean mass of an atom of a carbon-12 isotope. Obviously, we've already discussed this definition, but I just wanted to pop it in again. So for ionic compounds, this is known as relative formula mass. Moles is a unit of measurement, and 1 mole of any substance contains 6.022 times 10 to the power of 3 atoms, which is also known as Avogadro's constant. This is something you should know from GCSE chemistry, but obviously you might need a little refresher. When under standard conditions, gases and volatile liquids follow certain trends. Pressure is proportional to temperature, volume is proportional to temperature, so pressure and volume are both proportional to temperature, and pressure and volume together are inversely proportional, aka the ideal gas equation, which is in the top right corner of this slide. So empirical formula is the simplest whole number ratio of each atom in the molecule. Chemical equations must be balanced before they can be used in calculations to ensure the reacting ratios are correct. Note, it is desirable to have a high atom economy in industrial chemical processes to make it more economically viable and is better for the environment. So less waste product, less energy. So obviously you can see here all the key equations at the bottom. So moles is mass over MR, or also concentration times volume divided by 1,000. And also as part of the figuring out the ratio, so the MR molecule divided by the empirical MR gives you the multiplier. You got percentage yield, which is one thing that may be asked, and also percentage atom economy. So the percentage yield is basically how much of your products is actually your desired product, how much you're actually achieving compared to what we would experimentally want to see. And then the percentage atom economy, so how much the product is compared to the reactants actually of your desired product. Now looking at bonding and structures, there's quite a lot on here. So ionic bonding, so this occurs between a metal and a non-metal as electrons transfer from the metal to the non-metal to achieve full outer shells. When the electrons are transferred, it creates charged particles called ions. Oppositely charged ions attract through electrostatic forces to form a giant ionic lattice. For example, NaCl, salt, sodium chloride. They're all different ways of saying that. You've also got some key ions in the top left corner, which are really, really important to remember. They'll just really help you out because they're things that commonly come up. So knowing, for example, the ionic charge will just help you so much with certain questions. And then you've got covalent/dative bonding. So covalent bonding is between two nonmetals where electrons are shared between the two outer shells in order to achieve a full outer shell. Multiple electron pairs can be shared to produce multiple covalent bonds. These can be represented using dot cross diagrams, which I'm sure you're well aware of by now from GCSE. Dative bonding is when both electrons in the shared pair are supplied from a single atom. An example of this is NH4+. Once formed, it is treated as a standard covalent bond as it reacts in the same way. Then you've got metallic bonding. So this consists of a lattice of positively charged ions surrounded by delocalized electrons, producing a strong electrostatic force of attraction. The greater the charge on the positive ion, the stronger the attractive force, as there are more delocalized electrons. Larger ions, for example barium, produce a weaker attraction due to a greater atomic radius. Now specifically looking at different structures, so you've got ionic structures, so high melting and boiling point, strong electrostatic forces. When molten or in solution, these can conduct electricity as the ions separate and the electrons are free to move and carry a charge. However, these are often brittle and break into fragments when the layers of alternating charges are distorted. Then we've got metallic structures, so these are a good conductor due to delocalized electrons, and these also prevent fragmentation as they move around the lattice. Malleable, these substances are quite malleable as the layers of positive ions can slide over each other, but there is strong electrostatic forces, so high melting point, and are nearly always solid at room temperature. Then we have simple molecular, so covalently bonded molecules held together by weak van der Waals forces, low melting and boiling points, and very poor conductors. Water is simple molecular, but has a higher boiling point due to hydrogen bonding also being present, which we will discuss a little bit later on. Then you've got macromolecular structures, so this is basically covalent bonding into a giant lattice structure, so providing a high melting point. They are rigid, so examples of this is diamond, which is made up of 4 carbon atoms like bonded together, or like one carbon atom bonded to 4 other carbons, and then carbon is bonded to 3 other in flat sheets. Oh no, apologies. Oh my god, right. Let me start that again. So diamond is made of carbon, which is bonded to 4 other carbon atoms, and then you've got graphite, which sees a carbon atom bonded with 3 other carbons in flat sheets with free electrons between these sheets, which can conduct electricity. But a little bit more about the bonding. So this is more about the actual shapes of molecules and why they are the way they are. So the shape of a molecule determined by the number of electron pairs around the central atom as they naturally repel each other, so the largest bond angle possible exists between covalent bonds. Lone pairs provide additional repulsive forces, so for each lone pair, the angle is reduced by 2.5 degrees. The shape of a molecule can be determined by considering the type and quantity of electron pairs. So find the number of electron pairs and determine how many of these are bonded or lone. So you can see in the table here, you've got linear, which gives you with 2 bonded pairs and a bond angle of 180. Then you've got V-shaped, so 2 bonded, 2 lone, to give an angle of 104.5. And then, so it's probably easier for you to read than for me to go through them all completely. But obviously you've got trigonal planar, triangular pyramid, tetrahedral, trigonal bipyramid, and octahedral. So these are all really important for you to remember and just assess the fact whether it's got lone or bonded pairs. Then we have bond polarity and intermolecular forces. So the negative charge around a covalent bond is not easily spread around the orbitals, and every atom has electronegativity, which is the power of an atom to attract negative charge towards itself with a covalent bond. This power is different for every atom based on its size and nuclear charge, increasing along a period as atomic radius decreases, and decreases down a group as shielding increases. If 2 atoms that are bonded have different electronegativities, a polar bond forms, and the more electronegative atom draws more of the negative charge towards itself, producing a permanent dipole. However, you also got induced dipoles, which can form when electron orbitals around a molecule influenced by another charged particle. So you can kind of see here, so on the left-hand side, you've got a permanent dipole, and then on the right-hand side is what an induced dipole will look like. Then for the intermolecular forces, there are 3 types you need to know. So van der Waals, so this is the weakest type of intermolecular forces, acts as an induced dipole between molecules. The larger the MR of the molecule, the stronger these are. Straight chain molecules have stronger forces as they can line up and pack closer together, so reduces distance. Then you've got permanent dipoles, so this acts between molecules with a polar bond, attract each other and hold molecules together in a lattice-like structure. Then we've got hydrogen bonding, so we spoke about this a little bit earlier, hence why water has a slightly higher boiling point. So this is the strongest type of intermolecular force, only forms between hydrogen and 3 most electronegative atoms, so nitrogen, oxygen, and fluorine. The lone pair forms a bond with a hydrogen atom from another molecule, represented by a dotted line. Much higher melting and boiling point for this. Then we have energetics. So for bonds to be broken, energy is taken in from the surroundings, and when they are formed, energy is given out, and the overall energy change of the reaction depends on how much energy is transferred in these processes. Enthalpy of formation is the enthalpy change when 1 mole of a substance is reduced from its elements under standard conditions. There are certain symbols for all these different terms. There's a lot of different enthalpy terms that you need to know. And so it's really important you try to remember these symbols. Enthalpy of combustion is the enthalpy change when I assume that is 1 mole, but I've just messed up completely. 1 mole of a substance is burned completely in oxygen under standard conditions. Enthalpy is measured under standard conditions of 100 kPa pressure and temperatures of 298 Kelvin. Different covalent bonds require different amounts of energy to be broken, which can be found experimentally with calorimetry and because of variation figures in books. Because of this, figures in books tend to be average. Really apologies for what's going on with my ability to talk today. So calorimetry is an experimental method where temperature change is measured over time and then plotted on a graph. So measured change in temperature is proportional to the energy change. It depends on the specific heat capacity though of the substance, which is the energy required to raise 1 gram of a substance by 1 Kelvin without a change of state. Enthalpy figures aren't completely accurate as energy is easily lost via conduction or convection, and as well as inaccuracies in measuring temperature. So you've got some key equations here which are really useful for you to know, and then also kind of how it would look on a graph. Then we have Hess's law, so energy in a system must be conserved, therefore overall enthalpy change for a reaction is the same regardless of the route taken. This law can be used to calculate an enthalpy change using given enthalpies of formation as well as enthalpies of combustion. So bond enthalpy data is an average value for the energy required to break 1 mole of the stated bond in a gaseous state under standard conditions, and the reaction arrows always point towards the central product. So here's some key examples. The third one is an example for combustion, so how that would look. But yeah, have a look over this. Feel free to pause the video and just kind of have a look at how they are, what they mean. In the case of the second one as well, they are depending on the actual direction of the arrows and the reaction process, sometimes there will be a minus in there. It just really depends on the direction that the arrows are going and the actual direction of the reaction. Then we have kinetics. So starting with collision theory, reactions occur when particles collide, and for the reaction to occur, these collisions must have energy greater than or equal to the activation energy, and the particle orientation must be correct. So that's a new part for the A level, is that obviously the particle orientation wasn't something discussed previously. The conditions of the reaction are also very important. So you can see here on the right hand side, you've got a Maxwell-Boltzmann distribution display, which essentially not all molecules have the same amount of energy, and this kind of shows how it's distributed and how many of those molecules actually have activation energy. Changing conditions can alter the shape of the curve and how many molecules have activation energy, but the total area underneath the curve must remain the same, as obviously this represents the number of molecules in a sample. If temperature is increased, this increases thermal energy, which transfers to kinetic, and so more molecules reach activation energy and collisions are more frequent and successful, so rate of reaction increases. So you can see on the right hand side in that middle graph just how increasing temperature sees more molecules reaching activation energy. Increased concentration and pressure means molecules are packed closer together, so collisions are more likely, and so rate of reaction increases. So it doesn't necessarily increase the amount of energy they have, but just means that, collisions are more frequent. Then you have catalysts. So this is the bottom graph, you can see the difference. So catalysts basically work by providing an alternative route with lower activation energy. Therefore, the shape of the distribution doesn't change, but the actual activation energy shifts, so it becomes lower. So collisions are more likely to be successful and increase the rate of reaction. Then we have Equilibria. So some reactions are reversible, represented with a double arrow, and in each reaction system, one reaction is endothermic and the opposite is exothermic. These will eventually reach dynamic equilibrium, where the back and forward rate of reaction is the same and remains at a constant rate, but this can only occur in closed systems where there is no other substances influencing the reaction. We have Le Chatelier's principle. So when a system is subject to change, the system will alter to lessen the effect of that change. Useful when it comes to industry trying to maximize the yield of a desired product. Increasing temperature favors the endothermic reaction as excess heat needs to be removed, and decreasing temperature favors the exothermic reaction. Reminder that if enthalpy change is negative, then the reaction is exothermic. Increasing pressure favours the side of the reaction with fewer moles to relieve the buildup of pressure, and increasing concentration favours the reaction that produces the products and increase the yield of these. Catalysts do not affect the equilibrium as they affect the back and forth reactions equally. For reversible reactions, there is an equilibrium constant, Kc, that indicates the position of equilibrium for a reaction at a certain temperature. The concentrations of the substances need to be known to calculate this. So basically, the capital letters is the concentration of that substance, and the lowercase is the moles. So that's talking about the equation at the top. So where it's capital, that's actually the concentration, and the lowercase is the moles, squaring it. Well, not squaring it, but you know what I mean, to the power. Kc has varying units, so you can also place these into the equation to calculate its units. The value of Kc is not affected by concentration change or use of a catalyst, however it is affected by change in the reaction temperature, as the equilibrium position change results in different concentrations of reactants and products. Then finally we have oxidation, reduction and redox equations. So reminder of oil rig from GCSE, so oxidation is loss and reduction is gain of electrons. Oxidation and reduction occur simultaneously in a reaction because one species loses electrons, which are then donated and gained by other species and so are known as redox reactions. Oxidation number gives the oxidation state of an element or ionic substance, and allocation of oxidation state to a species follows a number of rules. So firstly, oxidation state of an element is 0. Oxidation states in a neutral compound add up to 0. Oxidation states in a charged compound add up to total the charge. Hydrogen has an oxidation state of +1. Oxygen has an oxidation state of -2. All halogens have an oxidation state of -1. And group 1 metals have an oxidation state of +1. An oxidizing agent accepts electrons from the species that is being oxidized, therefore gains electrons and is reduced, and goes through reduction in oxidation number. A reducing agent, on the other hand, donates these electrons to the species being reduced, and so loses electrons and is oxidized, and sees an increase in oxidation number. Half equations are used to show the separate oxidation and reduction reactions that occur. When writing these, you want to make sure all the species are balanced except oxygen and hydrogen, then balance oxygen using H2O, and then balance hydrogen using H+ ions, and then balance changes using electrons. Half equations can be combined in order to determine the overall redox reaction. So you can see here an example of copper and silver. But that is everything for part 1 of physical chemistry. Physical chemistry part 2 is incoming. And again, before you head off, please make sure to subscribe, comment below any questions you have, and of course like the video as well. And I shall see you soon. Bye.